Okay, welcome back. So we're going to now start the afternoon 2 talks. So the first one I get to introduce is Christopher Young from Stanford University, who's been majoring in plasma physics, thermal sciences. Advisor is Mark Capelli. His premium, or where he did his practicum, was again at Lawrence Livermore in 2012. Yes, it gets to be a theme right now. Yes, we see the shaking, we see the approval in the bags. Again, and making sure the title's still the same. So today we'll be hearing about tracking plasma dynamics with time-resolved laser diagnostics. So, Chris?
We're good to go. You hear me in the back? Cool. So thank you very much for the introduction. I'm going to talk to you a small part of my PhD research I recently defended about a month ago. And yes, my advisor is Mark Capelli at the Stanford Plasma Physics Lab. So to motivate this, really, plasmas are unstable. I know anyone who works with them knows that. There's all sorts of waves, instabilities, dynamic behavior that's going on. And really, to get the most information we can, we really need time-resolved diagnostics to really get at the fundamental details of what's going on inside some device, and then study how that evolves in time. So just to motivate that, this really awesome video just came out of our lab. It's plasma Schlieren of this coaxial plasma gun. And they're using a 10 million frame per second camera. And you can see all this really rich detail in the vortices and the turbulence that's going on. So that's really cool. Not the system I'm going to be talking about today. The type of optical diagnostic that we used is called laser-induced fluorescence. And sort of unlike the nuclear spectroscopy that we heard about from some of the other talks this morning, this is going to be in a slightly different range. And we're going to be talking about infrared transitions of electronic excited states of heavy atoms like xenon and krypton. And the advantage of this is that, first, we can get at some time-resolved properties with physical probes, like emissive probes, or Langmuir probes, but you can only go so close to the discharge. So like this photo up here of a NASA Hall thruster, which is a space propulsion device used to move your satellite around once it's already in space. You can see this probe up here is about ready to burn out. And so with these physical probes, you can only get so close before you start perturbing the physics that you're trying to measure. So instead, we can use optical diagnostics where you're just using light interacting with the plasma to measure what you're interested in. And so laser-induced fluorescence is a very spatially resolved kind of diagnostic. And we can measure all sorts of things like velocity distributions, species concentration, right? So it's species specific. And this all comes from the particular shape and position of this laser-induced fluorescence excitation spectrum. So all the data we get out from this is going to be some sort of peak that looks like this, and I'll tell you more about that. So the outline for the talk today is I'm going to tell you specifically about our method that we developed and how we get time resolution from it. I'll show you a little bit about how we validated it, made sure the method was telling us something real, and we trusted the results. And then I'll show you just a representative sample of some of the results we got. And in this particular application of Hall thrusters, which is what our Air Force sponsors were interested in, but I think these sort of techniques could be useful for other types of plasma discharges and maybe even other discharges outside of the world of plasmas. So to start, LIF, really at the most basic level, is absorption of a photon. You kick up your atom into an excited state, and again, we're talking about electron excited states here. And then sometime later, that atom will decay back down. It doesn't have to be to the ground state. It could be to another excited state, and it'll emit a photon. And so these fluorescence photons are what we'll be collecting for our signal. And the particular type of plasma conditions that we're going for here, as I mentioned, was heavy atoms like xenon and krypton. And these excited state electronic transitions fall in the infrared. And they happen to have a certain width that looks like this. And if there are ways to use a pulsed laser to get at some time resolution, but if you look at the typical line width of this pulse laser, you'll see it's about the same spectral width is the line that we're trying to measure. And so if you really want to get good spectral resolution, we're sort of forced to go to a continuous wave laser, which has a much narrower spectral line width, so we can scan across that transition and really get at that spectral resolution. But now, since we're using a continuous wave laser, we need some other technique to get at our time resolution. So some nice PowerPoint illustrations, right? We're going to put the laser in. We're going to pick a transition that has some target. So we're going to supply light at this wavelength, and then we'll wait for the fluorescence photons to come back out, and we'll collect that light with a photodetector, like a photomultiplier tube. But unfortunately, it's not quite that easy because there's a lot of background light. And there can be 1,000,000 times as many background photons as the photons that you created with your laser, right? So in order to pull out your signal, the photons that you created out of this big, broad, spectrally background bright stuff, we use a chopper. So by chopping the laser beam and sort of putting this blinking frequency on our photons, we can then use a lock-in amplifier, lock into that frequency, and distinguish our laser-induced fluorescence photons from this bright background. So that's sort of the general idea of how LIF works in these plasmas. There's another cool trick you can play if you want to get at the velocity of a flow. And that has to do with the Doppler effect, which is the same thing that makes the ambulance pitch change as it drives past you, right? That if you have a stationary atom, you put light in right at that particular wavelength where it absorbs, and you'll get a nice fluorescence feature like this. But let's say that that atom has a velocity in the direction of the laser beam. That atom is now going to see a slightly shifted frequency. And so you have to detune your laser in the redshift direction if the atom is going towards you in order to get that atom to absorb. So what we end up seeing is that there's a shift away from that stationary level where the stationary atoms would be, and the amount of this shift corresponds directly to the velocity of the atom. So I spent years in my PhD sort of measuring a bunch of these things and just trying to figure out how much it shifted over to get at the velocity distribution of the flow. And it also works if the atom is going away from you. You just have to blue shift the laser a little bit. So in summary, for the LIF method, right, we're targeting one species. So you usually need one laser per species. You pick out a target transition. We're going to scan the laser across that fluorescence transition, build up the fluorescence line shape. And again, you can get things like the most probable velocity, the relative peak height, sort of the more ions you have, the more fluorescence photons you will detect, right? So we can use the relative peak heights to get at the density or concentration of the absorbers that are present. And again, the peak shift tells us something about the velocity. In some cases, we'll have one main ion population. In some cases, we might have two populations, and that would come up as two peaks. All right, so here's just an overview picture of what the laser table might look like. This is just on the launch side. So here's our laser over here. We're going to send that light into the vacuum chamber. But there's also a bunch of other stuff here on this table. And all that's doing is measuring very precisely what our laser wavelength was as a function of time so that we can very accurately determine those shifts in the peaks. And we do that with two types of equipment. One, Fabry-Pro Etalon, which just gives a peak for a fixed step in wavelength or frequency space. So every 0.3 gigahertz I scan my laser, I get one of these peaks. And then we use an optogalvanic cell for the stationary reference. So we know where the zero velocity line is. We know how far we moved away from that line. And then that lets us determine our Doppler shift and, again, measure the velocity of the flow at that point in space. So now for the time-resolved part, right? We need, for at least the discharges that we use, we need about 6 minutes to scan the laser. We use a pretty high integration time constant on the lock-in to build up enough signal to noise to get a nice measurement. In order to get time resolution here, we need some sort of reference frequency. So in the discharges that I used, like a Hall thruster, you can look at the discharge current. And sometimes these instabilities or some dynamic properties arise where we get an oscillating signal, like in the discharge current. So rather than look and collect fluorescence light over all time, which would give you a time average measurement, the goal here is to really restrict the time interval over which we collect the light and sort of throw out all the other light that's occurring outside of that target time window, and then only send that into the lock-in. So here, if we had this oscillation in each set of these measurement gates, we would scan the laser and we'd come up with a separate fluorescence peak. And so that would sort of tell you, by lining all these up next to each other, that would tell you how the velocity is evolving in time over the course of this periodic oscillation. And to go a little bit more in detail, this is how we do this in hardware. It's all real time. First, we take our reference signal, like the discharge current. We use a voltage comparator to identify the beginning of each cycle. And this also gives us the advantage where it doesn't have to be a perfect sine wave where we know exactly the constant frequency. It can drift around a little bit, and that sort of opens up more applications to plasma discharges that can operate naturally without you forcing it to go at one particular frequency. So from there, we use a pulse delay generator to set up our target measurement gate. And again, we're going to get one of these per oscillation cycle. And then here's our photomultiplier tube signal. Again, if you sort of bypass all this, put that directly into the lock-in amplifier, we'll get one fluorescence peak, and that's the time averaged overall measurement. But by sampling the signal inside our measurement gates, we have two ways we do this. One, the sample and hold approach, where you basically average and then just hold a straight line, and that gets updated once per cycle. Or the fast switching method, where we basically open a switch, let the fluorescent signal through during that target time interval, and then we just zero it out, and we have no signal outside of that. And both of these methods ended up yielding the same sort of results. And there's also no reason that you have to only do this one at a time, because all the time information is contained in the signal, right? So we can do this in parallel, and so do different sets of those gates all along the oscillation. And this is a picture of our setup at the Air Force Research Lab in Southern California, Edwards Air Force Base. These are all custom-built circuits in our lab. Here we split the photomultiplier tube signal into each of these branches. They all get their separate measurement gates, and the big old stack of lock-in amplifiers that gives out that separate fluorescent signal in each one. And I was there around Christmas this past year, and we called this our Christmas tree of lock-ins. It's pretty funny. So how do we know that what we're measuring actually makes sense? We did a validation study on just a nice, simple 60 hertz spectral lamp. You might have these in your lab for some sort of calibration. We're looking at a metastable excited state of neutral xenon. And it has a nice, easy 60 hertz slow current oscillation. And we're going to compare this. Let's see, we're going to measure the time-resolved population of this state right here. And we're going to compare it to a simplified collisional-radiative model. And all the collisional-radiative model is doing is you're tracking the energy exchange through all the processes like electron impact excitation and fluorescence over time to see how energy is exchanged between all this. So here's the ground state down here. Here's the first ionization level of xenon. And here's some particularly strong, important excited states. And we're going to compare that between the experiment and the model. And so what we found is that both of our sample hold and the fast switch methods recovered sort of the same thing, the same sort of profile. But we found an interesting thing that actually ended up leading to new discharge physics that no one had seen before in this kind of lamp. And that was that the population of this state sort of had this funky shape to it. And what's particularly strange about this is, right, at the maximum current level here, when you're injecting the most energy into the plasma, you'd expect all the excited states to get populated at that time. But we see that as a local decrease in the population. And what's going on there is that we're actually exciting everything above here. So all the population of these states and the continuum, or the first ionization state, those are all getting populated, and we see that as a local decrease here. But then as the current starts to fall off and the energy starts to cascade back down, it falls through the state that we're measuring, and we see that as a local increase. And then when the current goes through 0 right here, the discharge actually briefly shuts off and quenches, and everything falls down back to the ground state really fast. And we see that as that big notch right there. And then everything sort of progresses symmetrically on the next half of the discharge. So that was something we sort of found by accident in the validation process. All right, so I couldn't do this talk without throwing in a little bit of rocket science. So we're going to talk about some Hall thrusters. This is an electric propulsion device. It's really low thrust, but is really high efficiency for the amount of mass that you carry. And we'll look at a couple examples of the types of really subtle physics that are going on inside this discharge that we can measure with this time-resolved method. So the main idea of a Hall thruster is you want to make ions. And we do that through electron impact ionization. And we will try to accelerate them as fast as we can, and that's producing thrust on our spacecraft. Here's your bit of rocket science. The rocket equation, the amount of delta V, the amount of velocity that you impart on your spacecraft from the propulsion system is proportional to the exhaust velocity and these mass terms. And so electric propulsion, we get to much, much higher exhaust velocities than in chemical propulsion. So that's where this is a valid competitive thing to do. So here's how one of these works. You'll notice we have some magnetic fields and electric fields going on. First, you add the propellant. In this case, mostly we use xenon, but there are also some alternative propellants that you can use. And that comes in at the base of this circular channel here. And then we also put it into our external hollow cathode. And we strike a little plasma discharge inside this cathode, and we extract electrons from that. And we're going to use those electrons to ionize propellant in our discharge. So there's a radial magnetic field that traps the electrons in closed drifts. So you tune that with an electromagnet to get a nice closed drift as the electrons go around. That both shapes the electric field and ionizes the propellant when a passing neutral comes by and gets smacked by one of these electrons. Once you make the ions, those get accelerated away by the primarily axial electric field. And you need to neutralize the beam. So actually 90% of the cathode electrons will end up neutralizing the beam. Otherwise, you end up charging up your spacecraft, and eventually this won't work anymore because your ions will just turn around and go backwards. So another particular characteristic of these thrusters is that they tend to work most efficiently in this sort of pulsed cyclical mode, and we call that the breathing mode. If you just looked at this with your eye, you'd see just steady discharge, steady glow in the vacuum chamber. But if you look at it with a fast light detector, you'll actually see that it's sort of blinking at you. And this particular thruster blinks at you at 50 kilohertz. And what's going on here is it's sort of like a predator-prey type interaction, if you're familiar with that, is we fill up the channel with neutral propellant. An ionization wave sort of goes upstream, ionizing all that propellant, making a bunch of ions. All those ions leave, and then there's sort of a downtime while we refill the channel with new neutrals. And so this sort of happens in a cycle, and we see that as this really strong discharge current ionization instability kind of thing. So here's a couple examples of stuff you can see with the time-resolved data that we really couldn't tell with just time average before. So one thing, we were just looking right outside the thruster point here, and we get a line shape that looks like this. And this is pretty broad, sort of interesting. We have a peak here around 9 kilometers per second, and then maybe something going on over here. But that's all you'd be able to tell with time averaged. But if we look at the individual time-resolved traces that are taken at different times along this current oscillation, right, you sort of see what's happening. So at 10 microseconds, there's this really tall, narrower peak that's going into producing this feature over here. And then at later times, the intensity is lower, so the local ion density is lower during these times, but they sort of get faster and more spread out. So this population over here is sort of producing that effect over there. So, in short, by having the time resolved, we can understand what's going on a lot better with these time average traces. And the time average only tells you part of the process. So we did this at a bunch of different points out in the plume of this thruster, and it was pretty cool. Journal of Applied Physics put our figure on the cover in December. And so the main thing that we were seeing is this axis is time down here, and this is velocity, and the color scale is, again, the LIF intensity, or the local number of ions that you have at that time. And there's some really strong oscillations. So if you just look at this point in space, you might see, for some times, ions going 5 or 6 kilometers per second, and at a couple microseconds later, all the way up to 15 kilometers per second. So there's like a really wide range in the ion acceleration that's going on in here, and also in the local density. Another cool thing we found was these double ion populations. So you have the main population of ions that are produced inside the thruster and accelerated out, but then there started popping up all these slower ions, and the origin of that wasn't really clear in the literature before this study. So again, here's the time average trace. You have the main population and then some slower ions. Maybe you would call that a peak, maybe not, sort of depends. But in the time resolved traces, right, each of these is taken at a different time. We see that the second peak sort of grows up for certain times and then goes back down. And so that was definitely something that you wouldn't be able to see without the time resolution. And this is subtle, but go with me. We can understand sort of what's going on with this pattern. So we saw the same pattern at 3 different points in the plume. So we're like, okay, something's going on here, and let's try to get at the physics. So here's a cross-section of the channel. Let's say that the voltage ramp looks like this. And as ions fall down the voltage hill, they're going to gain velocity. And so the point and the time at which we measure that velocity is going to determine where that ion was born and what the potential hill looked like at that time, right? So by looking at this, let's say we're taking the measurement here. The ion's born somewhere in the channel. It's going to fall down the hill, but not all the way. And that's where we make the measurement. And so we'll see that as the sort of local decrease in velocity right here. But then let's say there's this other population of ions being born outside the channel. That has a pretty big part of the hill to fall down right here. And so we could see that as locally being faster. But then let's say at a different time along the discharge current oscillation, that hill is located somewhere else. It's located more upstream. So now the same ions that were made up inside the channel here, now it can fall down the entire hill by the time we make that measurement. So we'll see that as a local higher velocity. And then same thing with these ions that were produced outside of the thruster. Only a little tail bit of the hill is left, so we're going to see those as being slower. So having the time-resolved data really lets us get into these subtle details of what's going on in the physics in a way that we couldn't see before. All right, so I'm going to switch thrusters really briefly. This is a commercial thruster that the Air Force uses on their actual satellites. It's manufactured by Busick Company. We're going to look all in the where all the action's happening inside the acceleration zone. So briefly, in time average first, here's the base of the channel. We're injecting ions over here. Here's the exit plane. You see the big bright spot is where all the ionization is happening. And then this it gains in velocity really quickly and then sort of moves out into the plume. And from this data, we can estimate what the actual potential hill looks like and what the accelerating electric field looks like. So we saw this in time average, but as usual, this is only part of the story. And so now by looking and plotting the time resolved data at all these points, we can really see the breathing mode. So sort of the yellow band is where most of the ion acceleration is happening, the sharpest gradient. And you can see it's moving up and down inside the channel over time. And that's something that people could only see in simulations before. This is, you definitely could not stick a probe all the way this far into the channel. It would just, shut the discharge off. And with that, we can now also calculate the time-resolved electric field, and you can see how it's also breathing. The magnitude and its position is changing throughout the discharge, or throughout the current cycle. And the last thing, you can do this at all sorts of different points. I did 2D data all around here. There's some really cool interactions here that I don't have time to talk about, where sort of the beams from the two sides of the channel overlap and start to interact in the middle. And so I just made this little visualization. This is experimental data. This is not from a code. And all these particles are just sort of popping up and sampling the local velocity field, and it sort of has all the main components of the discharge in here. So that was kind of fun. So to conclude briefly, I talked about this time-resolved method. We get really high resolution data in both space and time. It's applicable to more than just the plasma discharges. If you have a potential application where this could be useful to you, I'd be happy to talk to you about it. And we feel pretty confident that the methods are working as intended. And we were able to see some really subtle discharge effects in Hall thrusters, and we would be excited to apply this to other discharges to learn more stuff. So briefly, to acknowledge my collaborators at the Air Force and Stanford, and just thank you to Krell. This really is the best fellowship that we can get out there, and it's been a really great experience being here. So thank you, and I will take questions.